Okay. Hi, everybody. We're continuing our discussion of the first law of thermodynamics, and today we'll talk about heat transactions, right? Q in the first law of thermodynamics. And before we get into it, I want to talk about one issue, and that is what kind of variable is Q, the heat? Here's the answer. Heat is a path variable, right? Like work, different than temperature, volume, pressure. Path variables are ones which depend on the path between point A and point B and not simply the state of the system. And so we'll need to keep that in mind as we start working with this. There's another issue too, which is this. We could imagine perhaps applying some heat to a system and measuring the change in energy or something like that. But the challenge is that the first law of thermodynamics tells us that if I supply heat to a system, it could also do work. Right? These are equivalent ways to change the energy of a system. And so I need some way to make the work go away. And if you're clever, you can think about a way to do that. This is our equation for work. Work equals minus P external dV. And specifically, if we consider a scenario where dV equals 0, then work will always be 0. What do I mean by dV equals 0? Effectively, that means constant volume. Right? There's no change in volume. And if I do that, then the work will be 0. So one of the first things that we're going to have to do is recognize delta. I wrote this as a U, but I mean this is a V. Delta V equals 0. Right? And if I do that, that work term will go away. And it leaves me with an important equation right here. Delta U equals Q sub V. The change in internal energy is equal to the heat supplied at constant volume. Okay. Oops. This means constant volume. Again, this is important because heat's a path variable. This equation only applies if heat is, if volume is constant. All right. We need to get into this a little bit. We had previously defined heat as energy transfer due to a temperature difference. If I have two objects at different temperatures, I know that heat is going to be transferred from one to the other. We got to start to quantify this a little bit. And the first argument that I would make to you is that the heat transferred is proportional to the temperature difference. If there's a large temperature difference, my hands are so far apart you can't even see them. If there's a large temperature difference, there's a large heat transfer. If there's a small temperature difference, there's a small heat transfer. Pretty intuitive idea. Mathematically, we write that like this. This is a proportionality symbol. I don't know if you've seen that before, hopefully. I also hope that in your physics class you learned how to get rid of proportionalities. And the way you get rid of proportionalities is by inserting an equality and a constant. So I can write an equivalent statement which looks like this. Q equals C delta T, where this C is just some unnamed constant at this point. One more catch, which is, again, heat is a path variable. And so I need to specify what kind of path I'm talking about. And if I do that, I end up with an equation that looks like this. So heat's a path variable. We're going to talk about a constant volume path. Q sub V is equal to delta U, and this is equal to CV delta T. Right? Where this CV now has the name of a constant volume heat capacity. In words, what this says is that the heat that's transferred when the volume of the system is constant is the product of the heat capacity and the temperature change. Really, really straightforward. That was a little sarcastic. It's going to get complicated here in a second. But This is a really important equation and a good starting point. So let me give you a couple more notes on this constant volume heat capacity. Ignore this for a second. Look at this. CV is formally an extensive variable. If I had twice as much stuff, it would take twice as much heat to achieve the same temperature change. And so we can also talk about a molar constant volume heat capacity, which we're going to call CVM. CVM is simply CV divided by N, the number of moles. The other thing is, what does this mean, the heat capacity? And here's a mathematical statement. Rather than defining things in terms of delta differences, what we often define them in thermodynamics is in terms of differential differences. So I could write an equivalent statement as du equals CV dt, right? Or again, if I do some rearranging, I could say that CV is the change in U with respect to temperature when volume is constant. In other words, if I plotted internal energy on the y-axis, temperature on the x-axis, as I increase temperature, the internal energy would go up. And the heat capacity is simply the instantaneous change in the internal energy with respect to temperature. It's the slope. And if I knew what that slope was, then I could calculate delta U, W, Q, all of those things. We'll get there. That's a mathematical definition. Excuse me. Here's a more of a intuitive or a physical definition. I can rearrange my equation for QV and I get something which looks like this. And essentially this tells me that heat capacity describes a system's change in temperature when it absorbs some amount of heat. So if I have something with a really large heat capacity, it absorbs a large amount of heat and has a small temperature change. That is, that it has a large capacity to store heat. A classic example here is water. Conversely, something with a small heat capacity absorbs a small amount of heat and has a huge temperature change. It has a small capacity to store heat. The classic example here is something like metal. And you're probably familiar with these things, but one thing that I don't know if you've thought about is, why are these different? Why does water have a really large heat capacity and metals a really small heat capacity? And the answer is ultimately that they have different ways to store energy. Water has hydrogen bonds, it can move all around. It has all of these different ways it can store energy, whereas metals are fixed in these tight bonds and can't do a lot. So this will be important as we start to figure out how we're going to calculate CV. So I'm going to take a brief tangent here and tell you about the equipartition theorem. Atkins describes it in the Chemist's Toolkit 7, page 137. And here's what Atkins says. The equipartition theorem tells you that the average value of each unique quadratic contribution to a molecule's energy is 1/2 kT. So a couple notes here. K in this equation is Boltzmann's constant. It's given here in SI units. The second thing I want to tell you is that this is an approximation, and it doesn't always work. It comes out of classical physics, and it doesn't always work. So it's an approximation, but it's a reasonable one. We haven't talked at all about Boltzmann's constant. And it turns out that Boltzmann's constant is closely related to the ideal gas constant. Specifically, if I multiply Boltzmann's constant by Avogadro's number, you get R, the ideal gas constant. In other words, the ideal gas constant is the per mole version of the Boltzmann constant. This is per molecule, this is per mole. And so an equivalent way to say the equipartition theorem is that the average value of each unique quadratic contribution to a group of molecules' energy is 1/2 RT per mole. And if you're paying close attention, this should be familiar to you, right? Remember that for an ideal gas, internal energy is only dependent on temperature, right? So this is all consistent. All right. The issue now is, what do we mean by a quadratic contribution to energy? And again, here's this formal definition. It's a degree of freedom which scales as the square of some dynamic variable. Right? For example, velocity, momentum, something like that. Let me give you some examples, if I can get my cursor to work. Translational energy, 1/2 mv squared. Velocity is a dynamic variable, and the translational energy is scaling as 1/2 mv squared. Vibrational, you might remember something like this. Hooke's law, right? The amount of potential energy that's stored in a spring is 1/2 kx squared. Right? That's another example of a dynamic variable. There's one more: translational, vibrational, rotational. Right? Rotational is the other classical one, and there's equations for angular momentum and things like that. And so what we need to start doing is thinking about the different ways that molecules can store energy. So we need to classify molecules according to their type of ways that they can store energy. And there's, broadly speaking, 3 categories. So the first is a simple monoatomic gas. Example would be something like helium. A monoatomic gas has 3 translational degrees of freedom. It can move in X, Y, and Z. Next example is a linear polyatomic, something like N2. Right? Imagine my pen is nitrogen. A linear polyatomic, again, has 3 translational degrees of freedom. It can move in X, Y, and Z. It now also has vibrational degrees of freedom. So it can vibrate. And it has rotational degrees of freedom. Specifically, it can move this way, or it can move this way. The rotation this way, when I'm actually flipping it with my pen, is now called an indistinguishable representation. I couldn't decipher the molecule if it had rotated along that axis, so it doesn't count. Last but not least, we have nonlinear polyatomics. Water would be an example. 3 translational, it has vibrational degrees of freedom, and now it has 3 rotational degrees of freedom. It could now rotate along the axis. So if this is my water molecule, I could rotate this way. Use your imagination. All right. If you're taking notes, set yourself up a chart like this. We're going to actually now do this accounting, and we're going to count the different degrees of freedom and make predictions about the internal energy of these systems. Okay. Here we go. Helium. I just said helium is a monatomic gas. It has 3 translational degrees of freedom. It can move in X, Y, and Z. Can't vibrate, so it has 0 vibrational degrees of freedom. It can't rotate, so it has 0 rotational degrees of freedom. I add these up. I'm pretty sure my math is right. It has 3 total degrees of freedom. Remember that the equipartition theorem tells me that I get 1/2 RT per degree of freedom. 3 total, so this would lead me to 3/2 RT. And if I finally calculate the constant volume molar heat capacity, the derivative of this expression with respect to T, I get 3/2 R. Okay, nitrogen, 3 translational degrees of freedom. Right? It can move in X, it can move in Y, it can move in Z. How many vibrational degrees of freedom? If you stop and think about it for a second, it has 1. How many rotational degrees of freedom? Well, remember, this is a linear polyatomic. It can rotate in X, Y, but Z, this one, doesn't count because it's an indistinguishable rotation. So that one has 2. Add them up, check my math on this, but I'm pretty sure it's 6. I get 3/2 RT per degree of freedom. So that's going to give me 3 RT. When I calculate CVM, I get 3R. I take this derivative with respect to temperature and I get 3R. Water. 3 translational degrees of freedom, X, Y, and Z. Vibrational degrees of freedom. Now you might be able to figure this out, but you quickly start doing some accounting in your head and you're realizing it gets complicated. So there's a symmetric stretch, there's an asymmetric stretch, there's bends, some of them might be degenerate. Let's pause for a second. Let's do rotational degrees of freedom. Well, it's a nonlinear polyatomic. It can rotate in X, Y, and Z. So there are 3. And at this point, I'm going to give you a little hint, which is here. When multiple atoms join together to form a single molecule, the total number of degrees of freedom is conserved. This is the really important part. For example, 3 atoms come together to form a molecule, like water. Each independent atom, so 2 hydrogens and an oxygen, they're not bonded. They're just monoatomic atoms. They have 3 translational degrees of freedom. 3 translational per atom times 3 atoms gives me 9 total degrees of freedom. When those molecules come together and form the bonded molecule, the total number is 9. By process of elimination, 3, 3, I can infer that this is equal to 9, 3, right? 9 minus 3 minus 3. All right. That'll be useful when you get to more complex molecules. 9 total degrees of freedom, 1/2 RT for each, 9/2 R. Excuse me, 9/2 R. You should be able to determine predicted constant volume heat capacities for different molecules based on the equipartition theorem. One last comment, then I'll let you go. Here's what we predict for different molecules, and here's what we measure for the same molecules in terms of the constant volume molar heat capacity. What do you see? Well, with these really simple systems, it's pretty good. Right? Helium, argon, we're pretty close. But as they start getting more complex, we start to see greater errors. So this looks like it might be off 20%. We predict 25, we measure 20. If I have something like ammonia, I get to be 50% off. Like it's way off. So what's going on? Well, the answer is that vibrational modes are not a quadratic contribution to energy. And the reason is because they are not classical systems, but they're quantum mechanical systems. So vibrational modes are not, in reality, quadratic contributions to energy. And it will turn out that the magnitude of the correction will depend on both the temperature and sort of the frequency of the mode. Right? We may talk about this later in the course. How we're going to handle it moving forward is that either Atkins will explicitly state, calculate CV based on translation and rotation only, or it will give you a value. Use this value for CV. This is a big improvement on the old text, which basically said assume all assumptions, all corrections are 0. So I will stop there. make sure you take a look at the problem today. It's a good one. And I will see you next time for a discussion of enthalpy.